Hi guys, can you hear me okay? Check, check. Hopefully we're all good. Cool. So, do any of you have any questions or anything you'd like me to go over today? Any problems you've been running into or things that you've been curious about? Okay, looks like Sparker has a couple questions. Yeah, what might those questions be? I just saw a forum post, and I don't believe I got an email notification for that one, so sorry if I didn't see that one very promptly. Are the questions what you were talking about in that post or something new? Let's see, is it possible to plot points to keyframes to easier manipulate? I'm not sure exactly what you mean. Could you describe a little further? Instead of fixing pops with blend shapes. Oh, I see what you mean. You're talking about baking the simulation to actual keyframes for so you can see it in the curve editor. That's a good question. I've not seen anything like that. I do seem to recall there being might have been back at Blue Sky years ago, there might have been something used at the time. But yeah, I wouldn't know offhand what might be available for that. Yeah, I've not seen anything done like that. I'll ask around a little bit and see if I can come up with something. But yeah, I don't know offhand how one might approach that. So were there any other questions besides that that I might be able to answer a little bit more? I saw you had a question related to clusters breaking on impact with the ground. Is that the one? Okay. Did you have another question in addition to that, or that's the one you were about to ask? Okay, cool. Yeah, let's do that that Y-based constraint breaking. Let's see, we could use our main RBD sim for this. Yeah. Maybe I'll just grab a subset of that. Go to our bullet sim with constraints. And I'll rewind to the beginning of our timeline here. And I think I'll get rid of some of these objects to simplify this a bit. So let's maybe hide the monster and delete some of our geometry here. See, I'm just going to trim this down to a small section in Y. So let's drop in a split. And we'll, oops, pull up the parameters. We'll say at p.y is less than, let's see, I forget what the height of this building is. Looks like that's from 0 to 30. So I'll just isolate a slice, starting at, let's see if 10 is a good point. Actually, let's isolate just the clumped pieces. That's a good way to split out a lot of the pieces we don't need. We'll say at clump is greater than 0. And it looks like clump is a prim attribute, so let's set that. Okay. Yeah, this will serve as a pretty good example. Now in the DOPNet, let's set some initial velocity on this. So in here, in this case, I'm just going to temporarily disable this monster collider. And let's turn on the display for these RBDs. And on this RBD packed object, I almost never use this initial state in here, but sometimes when I'm just testing things or doing a demo, this is a nice easy way to get some initial velocity on there. So let's just push this and X a bit, do 10, maybe a bit of angular on everything. Let's see what this looks like. I'm not sure why we're not seeing our geometry moving. That's strange. Let's see, where's our display flag? Oh, that's right, because I thought none of our geometry was moving, but it's actually just this animated piece that's not moving, which is fine. I'm going to turn off the constraint visibility. I've never tried turning off the constraint visibility. I assume we can. Let's see. I would have thought it would be under guide options. Okay, we'll turn off show guide geometry there just to make this a bit more visible. All right, so by default, we'll just have these clusters maintain their clustering, no matter how hard the impacts are. This is still going a bit slower than I'd like for this demo, so maybe I'll trim this down a little bit further. Oh, I guess it's not too terribly slow. This will be fine. So let's pick a point in Y at which we want these to weaken. So we're going to use a solver attached to our constraint network to do that height-based breaking. So we'll drop in a solver. Let's see, where is that? A SOP solver, that is. Connect that to the third input of the constraint network. And in here, if you remember from the constraint videos, our constraint geometry is never going to update its position within this SOP solver network. It's going to update the data on this as the simulation steps through. You'll see all of the attributes on this updating. Let me just, so it looks like we have maybe, oh yeah, we did add substepping to this sim. I have 4 substeps on here now, so that's kind of a final quality level of substepping. So certainly for the sake of the demo, we can turn the substeps down to 1. This should go a whole lot faster now. Okay. Yeah, it does seem a bit faster. All right, so we don't want to change the Y position of these constraints, or change the position in general, because Bullet, it keeps track of the positions of the constraints internally, and it'll mess things up if we change that and output it from the SOP solver here. Let's create an output and connect our relationship geometry to that. And in the constraint videos, I showed you how to copy over the position data from the DOP geometry in order to get the constraint position to match the pieces so that we could do some extra tests, maybe break this with some geometry that we'll use to group our constraints and break anything that enters that region. But we don't need to actually update this to check the position. We can just look up the position in the dop geometry without changing it on our constraints. And I don't know why this dop geometry never seems to work unless I explicitly set a correct object mask. This default value just seems to evaluate to an empty string, it looks like. So let's change this to RBD packed star. So that will bring in any dop objects that are prefixed with RBD packed. And we can look up the Y position for our constraints. So let's do, let's see, a couple ways we could do this. Let's just create an attribute on each of the points, whether we should kill the corresponding constraint or not. So let's create a point wrangle and drop this on our relationship geometry. And let's look up the position for the corresponding named piece. So on our constraints, if you remember, each of those constraint lines has 0.0 and 0.1 with the name of the two pieces that it's attached to. So on each of these points, we can look up the matching piece by name. So for each point, we'll find the object ID from input 1. So let's connect this dop geometry to input 1. And we'll find the index of the matching name. So let's see, we want int index is equal to find attrib val from input 1. And if you're unsure of what the usage for a function is, you can always click on that and hit F1, and it'll show you the arguments to that function. So we need to specify which geometry we're querying, which will be the input 1 connected to the dop geometry. The class is going to be, as you can see here, point, prim, vertex, or detail. Then the name, and then the value that we want to find. So that's going to be a point attribute. So type in point, and we're querying that name attribute, and the value will be the current name attribute on the point that this wrangle is running on. And we can, instead of creating a local variable integer that will only exist within this wrangle, sometimes if I'm setting things up or demoing this, I like to set up attributes instead so that we can check it in the spreadsheet. So let's do an attribute by calling that I, and I'll call this ref index. And we'll check to see if this has logical values to make sure that it's finding the corresponding pieces in the dop geometry correctly. And let's see, it looks like, all right, I see what's going on here. So it looks like most of the constraints are finding the matching names because we're getting valid IDs here. The reason that we're getting all of these -1 values is because if it doesn't find that name in our dop geometry, then it'll give up and return -1. And we're not simming all of our geometry here. We deleted anything that's not part of a cluster, so that's why we're getting so many -1 values. So I don't think that really hurt anything in the pre-sim setup optimization. In the videos I had you remove any constraints that are no longer valid, that are connected to pieces that don't exist. So you certainly should do that. I'm not sure if it affects anything speed-wise, but it'll at least keep things a bit cleaner. But I don't think it really hurts to have those extra constraints. Probably won't have any ill effects. All right, so we can get the reference position. So I'll create a vector reference position, and that will be equal to a point lookup at input 1. We'll get the P attribute, and then the point we're getting the position of is going to be the ref index that we just looked up. And this should be an attribute, not a local variable. All right. So we've got the ID for the matching piece from our dot geometry, and now we have the position for the matching piece. Let's check our spreadsheet again to make sure that reference position is showing up correctly. Where's my spreadsheet? Not sure why that's not popping up. That's strange. Let's try going to the spreadsheet view here instead. All right, so it looks like it's getting those reference positions correctly, and any piece that's not found is just getting a reference position of 0. And we'll set the strength based on each of these reference positions. So I'll say, we'll create a new attribute. Maybe I'll create an integer called weaken, we can say. I'll say weaken, and then we'll use a conditional expression. We'll say at ref pos. So the reference position, we'll check the y value, and we'll say that less than a value of 5. So now we have this 0 to 1 value. So it's a value of 1 if that position is less than 5. 0 if it's not. So now that we have this per point value, ultimately we want all of our breaking to happen on the primitives. If you remember from the constraint videos, adding the constraints to that broken group is how we kill them in the sim. So let's promote this weaken attribute to prims. Do an attribute promote. There we go. And we'll go from points to primitives. We'll select this weaken attribute. And it's up to you if you want to only weaken it if both of the points in a constraint primitive go below the value of 5, or if you want it to weaken when only one of those does. It'll only be a very subtle difference. And you control that by choosing either the minimum or maximum value for that promotion to primitives. If you select, let's see if I'm remembering this correct. So weaken of 1, yeah, if you select a maximum, then if one point on a constraint primitive is below and weakening, and the other one has a value of 0 for weaken, then it will make the whole constraint line weak, since it's grabbing the maximum of those two values. If you set it to minimum, then it'll only set the primitive attribute to 1 if they're both below that threshold. So let's see, we could, I was going to say we could colorize this if we want to, just for some visual feedback. I'll add in a color stop. And let's set this to a ramp from attribute. Attribute will be weaken, class is primitive, and let's display that. And let's see, right now we have some point color on there already, so let's try removing that. So I'll drop in an attribute delete, remove that point color. All right. Now this should be checking, it should be setting anything below 5 to be weakened. Now our simulation's not up to date, so let's back up and start recooking this. And you can see we have lots of blackened constraints in there now because any pieces that don't exist in the sim, we're getting that reference position of 0, 0, 0. So those are all going to be considered weak. Let's see. Looks like Not sure if this is working. Let me try a blast instead of a color. Let's blast based on that weaken. Whoops, what did I just drop? I don't even know what that node is. Drop in a blast. We'll check the weaken attribute this way because we want to make sure that it's working. Okay, so this looks like it's working properly. So if we blast based on that weaken attribute, maybe I'll template display this other stuff. No, that doesn't make it any easier. So as our simulation pieces are falling down, you can see the lower portions are falling under that weaken threshold. So it looks like this is working correctly. So that's all good. And now that we know this weaken attribute is working properly, we can add that constraint to the broken group. So let's drop in a primitive wrangle. Or actually, you know what? I'm not going to add the constraint to the broken group. I'm going to give it a very weak strength. So it's up to you if you want this to automatically break below a certain Y height or just make it extremely easy to break. All of these constraints currently have an infinite strength of -1, so they'll never break no matter what. Actually, it looks like they don't all have -1. Looks like a lot of them have. All right, yeah. It's only the clusters that have -1. But those are really the ones we're interested in here anyway. So let's set a super weak strength on these. So we'll say if I at weaken, then we'll set f at strength equals, I'll just set it to 0.1 or something. And I'll call this weaken constraints. And let's check this to make sure it's actually setting some of these pieces to 0.1. So that looks like it's doing that correctly. That's all good. Now let's look, let's look at our actual simulation geometry. Let's back up our sim and take a look at these areas closer to the ground to see if it's obvious whether or not they're breaking up on impact. Hopefully this won't be too slow to sim. Yeah, it looks like it's going reasonably fast enough. Let's see. Doesn't look like they're breaking, does it? Oh yeah, maybe, I guess it does. I was suspicious of a few of these pieces that look like they're being held together, but it's possible that some of those are just big chunks of geometry, not unbroken constraints. Let's stop this for a minute. And let's step through to see if this is behaving as we expect. It looks like things are holding together a bit more than I would expect them to. Let's see. Let's try actually adding them to the broken group. Actually, you know what? Let's look at our guide geometry. This should show us whether the constraints are breaking or not. And this, I think, is getting a bit confusing with all of the pieces that aren't existing in the simulation. So I'm going to do a bit of cleanup on this. Let's set the scene to manual for a moment. I think our visual feedback is a little bit confusing with all of those unnecessary constraints. Let's see, where did I do that? I think it was under fracture optimize, where we have this little loop that will check the constraints and delete the invalid ones. So let's run that on these constraints just before the sim. So the constraints will go into that first input and then into the constraints null. And that'll be checking the geometry from the second input, number 1, So I'll connect that to our simulated proxies here. Now let's flip our display back to auto update. And let's see if this actually removes all the constraints we don't need. Should just take a moment, even though it's looping over 150,000 of them, it's still relatively fast. I guess it's kind of slow. Almost there. Any other questions while we're waiting on this? As always, feel free to shout them out anytime in the chat. You don't need to wait for me to, finish a demo. All right, so we have these constraints updated to only the ones we need. So let's go back into our simulation. And our display will be a bit more clear now without all those unnecessary constraints. And let's see, I was going to delete the hand section as well, but I don't think I'll bother. Yeah, it looks like these pieces are not breaking up. I thought that a strength of 0.1 would allow those to break extremely easily. So let's double check this, see what we might be doing wrong. Let's try, instead of setting the strength to 0.1, let's try explicitly breaking those below that Y value. So we'll say if we can, not only will we set the strength to something really low, whenever we want to do more than one thing based on an if statement, you'll need to add these curly braces. So I'll say at group underscore broken equals 1. All right, okay, now let's rewind our sim, jump out of this solver, and let's see if our explicit constraint breaking is working. Let's step through. Looks like we have a lot of constraints below y equals 5 that should be breaking, but they're not. Let's try a much higher y value. I'm assuming that 5 is a sufficiently high value to catch these things, but let's try just something that'll make the effect much more obvious. We'll check to see if the y position is less than 20 instead. So it looks like our weaken attribute is working correctly. Maybe our conditional statement should be. I can see that it is setting pieces in this broken group. Let's see what this warning is on the SOP solver here. Sometimes you'll see these fake warnings where it doesn't actually have any warning message to show us. I'm not sure what that's all about. This is really a bit strange because I can tell that it's working based on the feedback in our solver here. Bonus points if anyone can catch something I'm doing wrong. So we're definitely adding pieces to the broken group. I'm assuming it's not some silly problem like needing to reset the sim here. It looked like it was resetting itself when we just jumped back in the timeline. So that should be sufficient. Let's let this cook for a moment. All right, so looks like things are breaking. That's very strange. I don't know if we actually fixed it by resetting the simulation, because it looked like our sim was resetting when we rewound the timeline. But in any case, it looks like the braking is definitely working now, maybe a bit too aggressively. We're seeing everything below a value of 20, which is most of these constraints being broken here. Let's set that back to what we were using before. Set that back to a value of 5. You might want to pin your display to the stop net here so that the display stays there whenever you're diving inside the solver to make changes. You might find that to be an easier workflow so that you can see the results of your changes while still staying in the solver to tweak things. Huh, it's really strange. Looks like, I don't know if the value of 5 is just not high enough. It should be. Let's try resetting this again. So it almost looks like it's grabbing some sort of initial value rather than updating the position every frame, at least that reference position. You can see that it's deleted the constraints for these bottommost pieces here. This is going, for some reason my UI goes a little bit sluggish when I'm doing screen capture. I'm not sure why. See, it's not responding at all. It's very strange. Hopefully we're not going to lose our scene here. Sorry about the hold up here. It's being a little bit of a pain. Hopefully this will come back in a moment, but I'm just going to launch a new Houdini session just in case. That's weird. Don't know why we'd be running into license issues. Sorry about all the hiccups in this demo today. Oops. Sorry to run the wrong Houdini. We want the regular Houdini, not Indy or something. There we go. Yeah, it looks like this session is pretty done for. Don't know what, oh wait, looks like it came back. All right, our scene is still alive. Yeah, I'm not sure if it's something that just happens when I'm running these screen capture softwares, but yeah, it looks like it's frozen up again. Let's reopen the scene. Let's see, which one do we want? Live Spring 04. While I'm trying to revive this thing, and maybe I'll try to breeze through resetting that up again. Are there any other questions that anyone has? See, your excitement was too early, Rich. I don't know if this seems back or not. Seems like some sort of draw error or something. All right, let's see if this will let us save. All right, so at least we don't have to start from scratch if we lose this. Okay, I think we're back. Okay. Hopefully we're stable now. We'll find out if we're not. So stepping through the sim, see what happened to all of our constraints. Let's disconnect the SOP solver for a moment. Yeah, there's some strange stuff happening in here. It's hard to tell if I'm just running into display issues or if the constraints actually aren't there. Let's see what this constraint is complaining about. Yeah, I don't see any actual warnings when we pull this up. All right. Let's see if it looks like the constraints are working, even though it's not showing them to us. Okay, looks like they are. Let's connect the SOP solver and try to debug this a little bit further. Okay, so our weaken attribute is definitely working properly. And it looks like our broken group is updating properly as well. I'm not sure what else we would have to do. I don't know if there's any possibility we're running into issues with our DOP geometry input here, not updating properly, but it seems like it should be fine. Sometimes if I'm running into problems with the setup, I'll just rebuild it. Sometimes trying to debug things will take longer than just recreating it. So don't be afraid when you run into problems to just scrap something and recreate it if it's not an unreasonable thing to rebuild. Yeah, I'm kind of at a loss as to why we're not seeing our constraint geometry. Anyway, are there any other questions that anyone has while I'm experimenting with debugging this? Not seeing anything else in the chat at the moment. Rich is asking just more of a workflow question. Do you take the step-by-step approach on jobs? I assume you mean all of these different steps and the overall workflow here. I'm generally not this organized about it. I certainly wouldn't, go this extensive with labeling it. There's nothing wrong with doing it this way, especially when you're learning destruction. It's really good to break things into manageable chunks like this. But I do tend to have maybe a prep section separate from the fracture, or maybe I'll do them together. Yeah, I tend to not have it quite so compartmentalized like this. It also depends on if I'm just doing something that I'll be working on my own or if I'm handing off a setup to somebody else. But yeah, you can compartmentalize as much as you would like. Let's see. See if there's anything else we can figure out with this. It looks like it is working correctly. It's hard to tell exactly what's going on with our constraints because we can't see them. I'm guessing this is some sort of display issue because as these pieces are simulating, it looks like they're holding together reasonably well. Although we're not seeing any angular rotation on these. Let's double check the W that we're adding in our angular here. Let's try adding a whole lot more angular velocity to see if this is working. I'm surprised our simulation isn't resetting automatically when we make changes. I think I mentioned this before, but one thing I like to do to make it easier to reset the sim is to drop down the parameter view here, select the DOPNet, and pin that up there. And then I'll shrink this so we can just see that reset button. So now when we're working inside the DOPNet here, we can just hit this anytime we want to force that reset. And it looks like we're not really getting much angular velocity. So I mentioned before, my little trick for adding angular velocity to clustered pieces. And it seemed like clustered pieces were picking up some angular velocity if the entire cluster got the same value. But I'm wondering if, in this case, if all the clustered pieces getting that angular are kind of fighting with each other and not able to rotate much. Actually, yeah, let's go a little bit more extreme with this just to see if it's working or not. Try 200 in Z and step through. Okay. Looks like we're getting something a bit more reasonable. And this also will help us to test our cluster setup a bit better, because when we have more angular velocity applied, then you would expect these pieces to completely split apart if they weren't constrained together properly. So that does go to show that the pieces weren't just clinging together because they had the same velocity. It looks like our constraints really are working, even though it doesn't look like it here. So I think we've set this up all properly in our SOP solver. All of our constraint breaking on impact seems to be correct. This seems like, yeah, primarily some sort of display issue. All right, so I think we've drilled on this example for long enough, probably, unless there are any more questions about what I've done here, or any other curiosities you have about setups like this. Yeah, it looks like that's all working proper. See if there are no other questions, then we could take a look at using grains for our debris sims. So in the debris videos, we go over using RBDs for the debris and instance particles. And usually we'll use one of the two. Grains don't seem like they're used as often, but they're an absolutely valid way to do debris if you would like. Now, the nice thing about grains is that they're faster than RBDs because it's not calculating all of these complex collision shapes, but they're smarter than particles. So grains will give us some nice self-collision that we don't get out of a particle setup. So if we go to our week 6 debris tests, and let's stop this from cooking whatever it's trying to cook, rewind the sim, and I'll go to this instance particle setup. And I'll solid template these RBDs. All right, so let's step through here. Now these instance particles aren't going to collide with each other at all. And if you had some sort of recessed terrain or somewhere where you'd expect the debris particles to collect and pile up, that's not going to happen with instanced pop particles. They'll just all form a perfectly thin layer. Now, if we want to add some grain behavior to this, you can use pretty much everything the same in your setup. And just after our pop source, where we're adding any other pop behavior controls that you want to, where we currently have our pop drag spin, our particle limits, and the wrangle, you can also add in a pop grains here. And this will enable all of that self-collision. And perhaps instead of a ground plane, we could use some sort of, a a concave geometry that will collect that all the debris so we can see that it is working correctly. So let's try that. Give this some sort of a different collider. Maybe I'll just do, I'll try a tube, see if that works. Display that. Shift this thing into place. Make this a little bit bigger. I know we don't have a lot of time left, so kind of, you know, down to the wire on this little example here. I'm not sure why this is showing up so transparent. Looks like I'm having a lot of strange display things going on today. Yeah, I don't know why that looks quite like that. That's pretty weird. This should be displaying, oh, I've set this to wireframe accidentally instead of my normal display. Must have been when I was clumsily clicking around trying to bring my scene back to life. I guess that explains that. So let's create some end caps, make this a little bit wider. And actually, you know what, let's just do this with spheres instead. It'll be a little bit more obvious, I think. So this sphere, we're going to set this to a polygon. Set that to wireframe unshaded. We'll give this a much higher frequency. And let's grab some points. Sorry, the chat window's a little bit in the way here. We'll grab some points at the top. And I'm going to soft transform that down. Like so. Give this some soft radius. All right. This should be enough to show us that self-collision is working, I think. We'll find out. All right, so I'm going to add this to the DOPNet, to an extra input here. We'll add in a static object. So we already have a static object here for our collide. Yeah, we'll add a new static object and point this to, actually it looks like this is forcing us to use a SOP path instead of a connected input from the DOPNet. So I'll just give this a quick null. I'll call this bowl. And point this to ///bowl. And if we rewind, we should see that popping up now. Okay, cool. And let's start stepping through the sim. And let's see what the default grain settings give us. We'll probably need to change the P scale and such on this, but we can just see what it looks like as a starting point. We're going to need to get rid of our ground plane as well. So I'll just bypass that. Maybe I'll move this into place a little bit better. Sorry, I know this. Some of this setup is probably not the most exciting part. I'm trying to not spend too much of our time on this part here. All right, that'll do. Now let's, I suppose that we can view our actual instance bits. And I'll template view our bowl. All right. Looks like this is going a little bit slow. This might be a bit more obvious if we increase our P scale by quite a bit. So let's do that. Maybe I'll just lower the scatter on this so we don't have quite as many pieces. And I'll use some spheres as colliders because that'll be faster for the sake of our demo. So I'll connect that sphere directly there. Maybe I'll lower the density scale to just 1. This should go, oh yeah, we're going to raise the P scale as well. So just before the dot net, I'll add a point wrangle. The F at P scale times equals 4, we'll try. All right, that looks a bit extreme. Let's go with 2, see what that looks like. All right. Now this should be enough for us to at least see if that's working correctly. We mainly just want to see that our pieces are self-colliding and stacking up on each other. Looks like we have some default very sticky behavior, which doesn't look very representative of debris. Probably don't want our debris to be sticky like that. Let's take a look at what might be causing that. Let's get the sim to stop here. You can see that the self-collisions are working correctly, so that much is good. Let's see if there's something on here that would be causing those to stick instead of slide or bounce. All right, let's try turning this friction way down, see if that makes a difference. I'm also going to pin my display outside of the dot net. So I'll set that friction to 0.01, we'll try. Just want to see if it's less prone to sticking or if there's something else causing that. Let's check back in the chat window. Let's see, where is that? See if I'm missing anything. Any other last minute questions before we wrap up this session here? All right, looks like that hasn't affected our particle behavior at all. Sorry, I know some of this cook time is one of the downsides of doing, live simulation demos. All right, is this? I guess it is sliding. We'd have to play this back in real time to see if it looks like it's still sticking too much or if it's just, sensible given the scale that we're at. Yeah, I'm glad you find the troubleshooting good to see. I know I always say in these live sessions that I like it when I run into problems. Obviously, I don't like running into problems, but that's what the job is. The job is problem solving, and anyone who's done effects for more than the first moments of opening the program know that the whole job is just troubleshooting why things aren't working while you expect them to. So I'm happy to be the guinea pig to show you all the different problems that you might run into. It's it's one thing to see how everything is set up and works in a perfect world, but you're not here for a product demo. You want to see all the things that could potentially go wrong. All right, it looks like, yeah, we'd have to play around with this a little bit to see if the amount of slide makes sense. Anyway, one thing that is not very obvious about these grains, and this is one of the reasons that I think many people don't think to use it for debris is that the default behavior isn't bouncy. Now there's I was looking into this with some people at work, and it's not a very obvious thing. The workaround that we came up with, well, at least that we found in our investigations on the internet, is that you can set an attribute called isPBD on all of these particles. Because you'll find that no matter what we set the bounciness to on our collider here, these grains will never ever bounce. They'll just stick and slide. And that's not what we would want. It's really not expected behavior. And there's nothing on the grains that will allow us to, well, I mean, there are tons of things that we don't have the time to go through all the different settings on our grains here. But if you play with these very extensively, then I doubt you'll be able to find anything that will allow it to bounce. But if you set, let's get rid of this pop wrangle and the drag spin on this. Let's just add in an extra pop wrangle. I just don't want any unexpected influences on the sim here when we're trying to do a raw grains test. But if you set this integer attribute isPBD on the pieces, if you set that to 0, that will enable some bouncing. So my understanding of what this attribute is doing is this will tell it whether or not to apply normal particle physics to the grains. And when we were presented with this fix to get the grains to bounce, we assumed it was not a real solution because isPBD equals 0 sounds like it's turning off grain behavior. PBD is just position-based dynamics. So if you're turning that off, you'd assume that self-collisions would not work and that you're essentially just turning off grain behaviors in general. But supposedly, this will still allow it to self-collide and everything, which is the main thing we want to get out of grains. But supposedly this enables bouncing as well. Now, let's try to play this back at speed. Doesn't look very bouncy. Let's try setting some more extreme bounce parameters on both our pop object and our static object here. I'll set them both to 10. See what that looks like. Whenever you're trying to see if something's working, it's just best to go with some extreme values just to see if it's having any sort of desired effect. Looks like it's not really enabling any bouncing. In any case, you can feel free to experiment with this for debris if you'd like. I don't typically use it because RBDs are really the best. And if we don't see it well enough, then instance particles generally suffice as well. Both of those are much easier to work with than the grains. But that said, it's always good to have lots of options available. And yeah, it's just another tool to have in your tool belt as far as troubleshooting shots and responding to any notes that you might get. So I know this is kind of a half-baked demo of grain things, but at least the idea is there in terms of how you can try taking an existing instance particle setup and working with a grains version of that for some more interesting collisions. So yeah, depending on your shot, you might find it useful. As I mentioned in the videos though, I do generally prefer RBDs for debris whenever possible. Yeah, it's going to be the most accurate, and Bullet really can handle an awful lot of tiny little pieces. It's a pretty fast solver, and yeah, if you're going to see the debris very well at all, I think it's absolutely worth using that. over any of the particle methods. So, are there any other last questions before we wrap this up for today? Nothing? As usual, if you have any questions or run into any problems, post on the forums or drop me an email. And yeah, I'll look forward to seeing everybody's updates and the next homework assignment. And good luck with all of this week's material. See you guys.